Hey guys, the Network Bear here. Hope you've been doing well. Finally, we've got the video for OSPF up and running. We're going to be discussing something that I love working on, and it is the OSPF routing protocol. We're going to be looking at it quite in depth. This is going to be a few videos in the series. It's not just this one video. So look forward to that. In this video, we'll just be covering the basics of OSPF, and we'll be setting up OSPF on a network just to see what it actually does and how it works and how easy it is actually to set it up. So it's a bit of an advanced topic. If you don't really want to go through the theory, I will put timestamps in the description so that you can just skip to the practical side where we actually set it up on the lab. But I highly suggest that you look at the presentation that I'm going to be doing, because I put some time into it and I'd really just want to share this stuff with you guys. Anyways, let's get into the video. Alright, so we're in the presentation, and I'm not one that generally does presentations. Usually I'm just doing the labs and talking about concepts while doing the lab. But I felt this actually needed a little bit more, let's say, love and attention, because I want to make sure that the concept drives home. So we will be talking about OSPF, or the Open Shortest Path First protocol, and we'll specifically be looking at this on RouterOS. But it is open standard, so don't stress about it. It really works the same on all networking equipment. That's what makes OSPF so awesome, because if you have a MikroTik and you have another device, you can use it between these devices and it should work fine. All right, so let's look at this. What is OSPF? So first and foremost, OSPF is a dynamic routing protocol, which means it is able to learn routes without you having to fiddle around and type in all of the stuff the whole time that you would need to do if you were doing routing statically. So that actually makes it a lot easier for you, because if you have a large routing table, you can just redistribute or send those networks out using OSPF dynamically without you having to set up static routes on each router. So this is really useful the bigger your network grows, because if you have like 20, 30, 40, 100 routers, it's a bit hard if you're just doing static routings between all of the devices. But with OSPF, it's almost like a click of a button, and then all of the routers know where everything is. It is an interior gateway protocol, which makes it very useful, because what does that actually mean? A lot of people don't actually know what IGP is, but it's basically for any routing that occurs within our own network, within our own cloud. So when I'm talking about a network, I'm not talking specifically about a prefix. I'm talking about our network. All of our routers, all of our firewalls, all of our devices that actually make a part of our network, they fall into what we call an autonomous system. And then an interior gateway protocol essentially allows for routing between these systems so that you can deliver awesome services as well. I'm sure you've seen some of my other videos where I talk about stuff like VPLS or MPLS, and IGP is what you're going to need to kind of use for services like that. And OSPF is an IGP. It is open standard, like I mentioned earlier. So this means it can be used between different vendors, because OSPF does what OSPF does. It works the same. It just might look different how you configure something, but it does the same thing at the end of the day. It is a link state routing protocol, very important. And what that essentially means is OSPF checks out what kind of bandwidth you have on your links, if the links are up or down, and then it will use what we call, I've got it listed down there, a Dijkstra algorithm, to kind of make sense of which is the best way to get to any specific destination. What's the shortest path? It works out something that we call costs, and then those costs would typically be taken into consideration before a route gets injected into the routing table. OSPF also builds what we call an LSDB, or a link state database. And that is in essence just a map that each router has that is exactly the same across the network. So this is also why you'll see later on in the video, we'll talk about stuff that we call areas. But if you have a small network, you could work on a single area. It's totally fine. But in essence, what it means is each router has its own link state database that it keeps up to date, and then it all matches across the board so that there's no missing pieces anywhere. All right. Now we're going to look at some OSPF terminologies, because it is quite important to understand, because a lot of the times you'll hear people talk about these things, but you don't really know what it is, because they just say it, but you know, you kind of need to Google it afterwards to figure it out. So I just thought I want to just bring up a few popular terminologies when we're talking about OSPF on router OS. And you'll see stuff like OSPF v2, which in essence just means it is IPv4 networking, IPv4 OSPF. You'll see stuff about OSPF v3, which relates to IPv6 networks. You'll see stuff about an AS, or an autonomous system, which I mentioned earlier as well. It's just a single entity that all routes within a single network belongs to. Then we get stuff like areas. Now, an area is quite interesting because an area allows you to split your autonomous system into different, what the word is, areas, different sections or zones or sectors, so that you don't need to have just one big area where all of the route calculations are being done, or all of the LSDBs are being updated. If you opt to use multiple different areas, it is quite nice if you scale your network and it becomes quite large, because maybe you don't want all of the route information to be updated in one single area, and you can cut it up into smaller areas, maybe half it, maybe make more areas, and then only devices in the same area will in essence communicate with each other or send each other link state updates and stuff. You will see more about that in a second. Then you get stuff that we call ABRs, or area border routers. Now these are in essence routers that have a very special job in the world of OSPF. They exist between different areas. So think about them as a toll gate almost, or as a border control or something. It's some place between two, I don't want to say networks, but it's two different zones, and then this router exists between both zones, so it's able to learn or distribute routes or updates between the different zones, which makes them very useful. Then you also get stuff called ASBRs, or autonomous system boundary routers, and they are connected to different autonomous systems. Now these are typically your internet facing routers. So if you work in an ISP and you do end up in a core network engineer role, you might have stuff like internet peering links or internet exchange links or stuff like that. So where your peering comes in to get onto the internet, those type of routers will in essence become your ASBR routers, because you will be learning internet routes on those routers, and maybe you want to tell the rest of the network how to get to those internet routes that aren't necessarily on your network, it's outside of your network, but you still want to tell the rest of your network how to get to those routes. So an ASBR typically has that function. All right, we're going to continue with some more terminologies. Stuff that you might hear a lot of people talk about is neighbors or neighborships. And these are in essence just devices that are running OSPF. It doesn't necessarily mean that because OSPF is running, that two routers are automatically just working. You can set up OSPF on both devices and they can be neighbors, they can see each other, but they're not necessarily exchanging routing information yet. If they need to do that or want to do that, then you'll see a new term that we call adjacency. Now that is when two neighbors become really good neighbors. They invite each other over for barbecues or whatever because they really like each other. Now adjacencies occur whenever two routers are forming a full type of connectivity with each other, and then they can exchange link state information. And now we get to the tricky part that a lot of people get very confused with OSPF. And in another video, we will be going over these in more detail. But then you start seeing stuff like LSAs, or link state advertisements, which in essence is information that's contained within a packet to tell the rest of the OSPF network what this is and what's happened on the network. If something's gone down, if a new network has been added, stuff like that would be contained in an LSA, or a link state advertisement. Then you get an LSU. Now, what the heck is an LSU? We just talked about LSA. Now, LSU is a link state update. So I want you to think of this as a transport mechanism, which I've highlighted here in the demonstration or the presentation. And what an LSU is, think of this as an encapsulated packet. So you'll get your normal packet, your IP packet, and inside it, you'll have your LSU. And then inside the LSU, your LSA is actually. So the LSU is just there to tell the rest of the network, hey, this is going to contain some routing information. But the LSA exists within an LSU. So these two kind of go hand in hand with each other, but the LSU is how it moves between different devices or between neighbors. And the LSA is actually the payload, the stuff that's in the OSPF configuration that needs to update in the link state database. Now we also have what we call a LSR, which might be confusing if you work with MPLS, but an LSR in this case is a link state request. So a router can look at its link state database, and if it feels like something is missing, it can request an update from the rest of its neighbors to say, hey, I'm going to send a link state request. I want to know, how do I get to this network, or what's the cost of this link, or what's going on here. And then because of that LSR, it can now receive an update from one of its neighbors to tell it what's going on. So it can actually become synchronized again and have the whole picture on its LSDB again. And then we get something called an LSAC, or a link state acknowledgement. Now, an LSAC is in essence the end of the communication between OSPF routers once they've sent their packets between each other to say which networks exist or what's going on in the LSDB. Because I want you to think about the three-way handshake as a TCP IP connection. You know, there's the ACK. We've got an ACK, a SYN, and a SYNAC. So it's kind of the same concept. You are going to request something, you're going to get something back, and then you're going to let your buddy know, hey, I did get it. Here's just an acknowledgement to tell you I got it. So that is what an LSAC actually does for you. All right, some more terminologies, tons of them. We've also got something we refer to as a DR, or a designated router. And this is, in essence, when you configure OSPF on its default settings, you'll see stuff like DR and BDR happening. But a DR is responsible for keeping the LSDB updated of all of the devices. So all of your neighbors will in essence form an adjacency with the DR router, a full adjacency, and then the DR will be responsible for updating the LSDB. So all of the neighbors don't update each other with what's going on. They will connect to a DR. The DR will tell them what's going on. And then they just have a central point where they all connect to and mesh to, instead of having one big mesh between all of the routers. Now, BDR does exactly the same thing as a designated router, except it only receives the updates, but it does not send any of the updates. Why this is because the BDR is there in case the DR goes down for whatever reason. If it just stops functioning, we need some type of a failover mechanism, a buddy to jump in to just help out in case there's some type of failure, because we don't want a large scale outage because a single node has gone offline. So that is what a BDR will do for us. We have things we call router IDs, which is in essence a unique 32-bit address. And it's an identifier of sorts that you can apply to your OSPF router to say what its name is, what its identification is. We also talk a lot about networks. So this might be the prefixes that you can advertise in OSPF to let the rest of the network know how to get to a specific subnet or prefix. We've got stuff like network types. Now this is quite interesting because you get different types with MikroTik, and we will go between the different types in another video, but the types will say if something is either being broadcast or if it's a point-to-point connection. Broadcast connections will have the DR and BDR nodes, whereas point-to-point connections will always have full adjacency with each other because you're just connecting to a point. All right, hang on, let me go back. Here's the last bit for the terminologies. We're also going to be talking about stuff like stub areas or an area type. MikroTik calls it an area type, but it is a stub type. And this sets how an area will operate, either its default stub or not so stubby areas. We talk about cost. Now, cost is very important because this relates to how OSPF will determine what the best path is across the network. Because the lower the cost is for something, just like on static routing, if you make your administrative distance lower, it's a preferred route. OSPF is exactly the same, but you don't see that in the administrative distance. The OSPF figures out in the cost what the total cost is to get to a specific prefix using a specific path. And if that cost is low enough, then it will inject that route into the routing table, and then you'll see it as an OSPF route, which will by default have a administrative distance of 110. All right, and then we will also be talking about stuff like priorities. Now, priorities is used in that broadcast process where routers are trying to figure out who is the DR, who is the BDR. So devices with a higher priority is in essence going to be elected as a DR or BDR. If you set the priority to 0, it means that router that you're working on will not participate in the DR/BDR event. It will just say somebody else is going to do this job. I'm not interested in trying to become the DR or BDR. All right. And now we have a few requirements to make OSPF work. Namely, devices need to be in the same area to operate, because you can set what the area is. And this is also what's nice about MikroTik. They do instance-based OSPF as well. So you can have multiple different instances of OSPF, and they can each have different areas. It's really cool stuff, which we'll learn more in the practical labs. You need to have your subnets need to match on your interfaces that you're going to be configuring the OSPF on. Your hello timers needs to match. Your stub flags needs to match. So that was that area flags we were talking about a little bit earlier. If you have one flag as default and the other one as stub or NSA, then you're going to have some issues with the OSPF actually working. Same with the network type. If you're using PTP, point-to-point, and you're connecting to a broadcast router, it's also not going to work. Your authentication needs to match as well, and that namely just means you can't set up stuff like MD5 authentication. Think of that as a password between OSPF routers so that they can authenticate to form a connection. It's just a safety mechanism, which is quite nice. And also the MTU needs to match for the neighborship to effectively take place. All right, how does OSPF function? Now, first things first, you need to enable OSPF on your routers. You need to have it running on your network. And these two routers ideally need to be either directly connected to each other, or they need to connect on layer 2 to the same place, maybe the same switch. And then from there, they can then start doing what we call the hello packets with each other. Now, the hello protocol is what will be used to actually do discovery. And it will, in essence, be sending out a hello packet over the interface that you've set for OSPF to discover your neighbors. Initially, that discovery is done with a broadcast message. And then after that, any new updates that is done on the OSPF network will be done using multicast on the 224.0.0.5 address. One also interesting thing, let me just go back. OSPF also runs on IP protocol 89. So if you look at your firewall rules on a MikroTik, you might see there's an IP protocol 89, which is OSPF. Make sure that you allow OSPF to run. You need to, if you have lots of firewall rules and you block it maybe by accident, then OSPF won't work. So let's continue. And then when a connection is established or an adjacency is formed, routers will exchange their LSAs between each other to basically populate the LSDB to let each other know where what is actually going. And then those LSDBs will then be synchronized and then be kept updated, where the routers will essentially be sending updates every 30 minutes just to make sure there's not been any changes on the network. But if a change does occur, if a link goes down, a router will then in essence just start and send out an LSU to say, hey, there has been a change, update your stuff. If a change occurs, like a link goes down, a better link becomes available, the router will generate an LSU to be sent to adjacent routers to update them on new changes. So that's also important. So if a new link becomes available as well, let's say you've got a bunch of 100 meg links between your routers, you install a new 1 gigabit link. The moment that gigabit link comes into effect and you've set the cost correctly, OSPF will then let the rest of the network know, hey, this is the better path. Let's go this way. It is important to note that LSDBs will be synchronized across the area. Important, the area, not multiple areas inside the area that you are working on. Here is kind of what the process will look like when the neighborship process occurs. And this I've taken from the IBM website, and I haven't seen an IBM site in years. So I was actually quite astonished to see something that I liked looking on the website. But in essence, what you'll see is we've got a hello packet coming from a router. The other router will receive it. It will tell you what the DR is, but it will send a hello back. So there's two hellos, and this is where we get the X start and the exchange happening. So this is kind of where we want our MTUs to be the same. And then we got a loading state, which is where link state requests and link state updates will be sent. And then we finally have that full state at the bottom, where your devices will in essence have the same link state database and only updates will make any type of changes on the link state database. All right. Here's also the OSPF neighbor states that you should be aware of when you work on router OS. You might see that your neighbor is in a full state, which means that essentially you've connected to a DR or to a point-to-point device, and your LSDBs are completely synchronized, so the routers know how to get to everything. You might see two-way, and two-way is not a bad thing. It just means that no LSUs are being sent between the routers. They've formed a relationship. It's a two-way relationship, but it's not to update anything in the LSDB. It's just to be aware of each other. Let's say your DR and your BDR goes down, the new DR or BDR could be elected, and that's something that the two-way connection could be there to facilitate. And then you might see a down, initializing, loading, start, exchange type of field. So that is either the OSPF is down or it's in the process of discovery. All right, so this covers the very basis of the OSPF theory. And now we're going to shift the theory to a practical lab where we're going to configure OSPF on some CHRs. And then in essence, what we're going to do is we're going to send out a default route to 3 of our provider routers, and we're going to do some route summarization, and you're going to see how cool OSPF actually is. So let's jump into that in EVE-NG now. Hey, we're back in the EVE topology, and it looks a little bit different since the last time we've been working on it, because what we've done now is we've actually added a switch to this topology where all 3 of our provider routers connect onto, so router 1, 2, and 3. They all connect using 192.0.0/29 to communicate with each other directly. And we've also introduced a backup link between router 2 and 3 using Ether 5, so we can set up a little bit of redundancy or failover purposes, so we don't just have that single uplink to our ASBR. So this is going to be a very limited or focused video, because we're just going to be working on area 1, and we're just going to be setting up OSPF on router 1, 2, and 3. The goal of this video will be to just showcase how we can configure OSPF on a router, as well as how we're going to redistribute a default route across the network. And last but not least, we will also add some routing on our router 2 and 3 so that we can dynamically learn all of our WAN uplink IP addresses, so that we don't need to, in essence, have a tough or hard time statically adding everything. So what I'd like to do is I'd like to navigate to Winbox, and I'm going to log on to router 1. All right, so we're in Winbox, and I'm going to give you a little bit of advice or a bit of a trick when it comes to working with any type of dynamic routing protocols. We will be introducing a loopback address to our topologies now, because we can use that loopback address to form connectivity or also to provide services. Because if we bind the IP to an interface, if the interface goes down, that means the router is no longer accessible on that IP, and then certain stuff might fail. So if you just add a loopback address and have devices connect to the loopback address for services like BGP maybe, then your stuff will just stay up, which is wonderful. So we're going to add a loopback address by going into our bridge, create a dummy bridge, call it LO0. We're not going to assign any ports to it. We're just going to assign an IP address to the bridge. So this will be my router ID that I want to assign to the OSPF in this case, which will be 255 for me. And I'll bind it to my bridge. And there we go. Now we can proceed with the OSPF setup. So to get to the OSPF, you'll navigate to routing, go to OSPF. And now here is where the magic happens. There's 4 tabs, ideally what you'll be working on most of the time, being the interfaces, instances, networks, and areas. We will work on stuff like the virtual links in a later video, but it's not necessary to understand how OSP works in general. So what I'm going to do is I'm just going to first look at my instances. And in the instances, there will always be this default instance with a default backbone area, which is area 0. On router OS 7, I believe it's not there by default. You need to add it yourself. And I'll make a separate video for router OS 7 again once there is a long-term release and everything's fixed. But yeah, it's a little bit different, but the concept still remains the same. All of the options are the same. It's just a little bit different how you access them. So what I want to do is I first just want to update my router ID on the instance. So I'll set my router ID to what I made it on the bridge. And the instances again are nice because here you can even create multiple different instances and even assign them to different routing tables, which is so cool. But we won't do any of that now. We'll just have a default routing instance with the backbone and the main routing table. So next step, what we're going to do is we're going to add our networks. We could add the interfaces as well. Actually, let's add the interfaces. I'll add a interface and then I'll add the network as well. Because what's nice is if you add a network and that network belongs to an interface that's going to participate in the OSPF, it will create a dynamic interface with some base settings already configured for OSPF. So that's quite nice. But let's just add a basic interface. Let's look at my topology. It should be Ether2. So I can see router 1 on Ether2 connects to the switch. So I'll say Ether2. Now I can give it a cost. So I can say the cost is either 10 or 1 or 100. By default, it's 10, and MikroTik has its own scales to use for the cost. But for any 1 gigabit link or up, you want to use the cost as 1. Let's say it's a 100 megabit link, then you want to use 10. If it's a 10 megabit link, use 100, etc. This is kind of just how the costing works. The thing with the lower cost is the one that's typically going to be preferenced for your connectivity. Your priority, this you will set if you want to make a router a DR or BDR. I'm just going to leave it 1 for now, and we'll change this after I've configured OSPF so you can see how it affects the DR and BDR election process. Authentication, here you can set stuff like the MD5 or a simple password. But we're not going to tweak anything else here. Here's also something, the use BFD. This currently, it kind of doesn't work that nice on version 6, but I think it doesn't work at all on version 7. But I could be corrected, maybe they fixed it already. But just one more reason why I'm not really showing version 7 stuff just yet. Anyways, we'll leave all of this stuff, the defaults, even the hello timers, and we will apply this. And what I'll do is, actually we're just going to have the one interface, so it doesn't matter. I can't really advertise stuff there, but let's just add the networks. And typically what you'd like to do is add your connected networks in here. So what I could make is 192.0.0/29, and that will be in my backbone area. And I will also just advertise my loopback address, which is 192.0.0.255. I'll apply that. And if I go to my interfaces, you can see that loopback address is passive right now. And we can see that the Ether2 is still waiting for something to happen. It's still waiting for a neighborship to be formed. So let's form one. Let's connect onto a different router. Let's connect onto router 2. And from router 2, we're going to essentially be doing the same thing. We'll be creating a bridge. So let's just zoom in. I'll create a bridge. Call this LO0. Add an IP address, which is going to be the IP that I'm going to use for the loopback or for the router ID. For my case, it's going to be 192.0.0.254. And this can be any address really, but preferentially make it something private and something that's not going to be in use. And now I'm going to go into my routing, going to go into my OSPF. I'll go into my instances. Now my router ID I want to set to 192.0.0.254. And I will apply this. I made 10 too many there. And here you can see the area, it's just the default area. But now I'm going to set the networks. So I'll advertise 192.0.0/29. And also I've got that redundant link between router 2 and 3, which is 192.0.0.8/30. So I'll also just advertise that. So 192.0.0.0/8. Apply that. And if I go to my interfaces, we can actually see it's created the dynamic interfaces now. So Ether1, which is going to the switch, and it's actually formed the neighborship with router 1. So I can see that by going to my neighbors tab. We can see what the router ID is, what it's connected to, as well as what its IP address is that it's formed that connection on, and on which interface and how many state changes there's been. We can also look at stuff like the LSAs here, but we're not going to go too deep into the LSAs now. We will have a separate video covering that. I just wanted you to see that we've created some dynamic interfaces here, but I do recommend trying to put your interfaces in a manual mode wherever possible, because it gives you more control. So I've just copied them and pasted, and now they're static interfaces. There's one more network I want to add, which is our loopback address, 192.0.0.253, or sorry, 254, apologies. And now I want you to see where some of the magic happens. If I go back to router 1 and I go into my routing table, I can actually see I'm learning some OSPF routes already. Awesome. I can see I know how to get to 192.0.0.8/30, and I know how to get to 192.0.0.254, which is the loopback address of router 2. And here I can see what the distance is, which is 110, which is expected of an OSPF route. Let's quickly see, can I ping 192.0.0.254? I can ping that. So we've got connectivity between router 1 and router 2. Now let's bring router 3 into the fold. So I'll open up another Winbox session, connect onto router 3, and let's zoom in. And now that I'm in router 3, same process, create a quick bridge. It's not needed, but it's recommended to do it this way. It's just more like a best practice type of thing. It will save you down the line, trust me. But if you want to, I don't want to say be lazy about it, but if you just want to use whatever interface IP you have, that is fine. It will work. It's just you might run into some issues further down the line. All right, so let's add our loopback address, which will be .253 on LO0. And now I'll go back into routing, OSPF. Let's update our router ID to 192.0.0.253. I'll add my networks, which is 192.0.0.0/29. I'll copy this, and then it's .8/30. And then also my loopback address, 192.0.0.253. Alrighty, so on router 3, I'm also just going to look at its neighbors. And now it's got two different neighbors on Ether 1. So it can see it can get to these two neighbors, which is 192.0.0.2 and 192.0.0.1, as well as what their router IDs are. And then there's also the neighborship to router ID 192.0.0.254, which is router 2 via Ether 5. So it's the backup link. Now I'm going to go into my instances or my interfaces, and here we can see again in the tab how many neighbors we have exactly, what the states are, all that wonderful, wonderful stuff. Now let's talk about how to statically set the priorities so that you can choose which router will be the DR as well as the BDR. And I'm also going to show you a little bit of a thing that usually gets new people on OSPF when they configure this stuff, because it's not totally clear, but it is in the documentation if you read about it. But I'm going to show you kind of what happens. So let's say we're on router 1. We want router 1 to be the DR or designated router. It is currently the DR, so we're kind of lucky with that. But let's say we always wanted to make sure that router 1 is the DR. So we could do this by just setting the priority of it a bit higher. So I might make this 10 because the other routers are still 1-1 on the priority. So I'm going to apply this and I'm going to wait for the connection to come back up. But I'm going to notice something when the connection comes back up. And we'll see it's currently a backup. What? Huh? What? Why? Why is this a backup? So something to take note of with OSPF, and this is just kind of how it works, is setting the priority doesn't necessarily mean if a OSPF neighbor goes down and comes back up that the original device that was the DR will resume its mantle. It will take its crown back and start doing stuff again. OSPF is just set up in such a way that there is a DR and a BDR, and as long as one of the two exists, it doesn't matter which router you want to elect. If you want to force router 1 to, in essence, become the DR in this scenario, then you could just either disable the interfaces and re-enable them all, and then in that election process at that time, when they first do those first hello discoveries, then router 1 will definitely become the designated router. But it's not the end of the world if router 2 or router 3 or any other router in your network becomes the DR or BDR. It's just something you should take note of, but I wanted to show you how you can use the priority to, in essence, say in the event of all of the devices having to go off and come back up, how you can make a router a DR. So this is more of a design perspective, but it's not the end of the world if router 2 or 3 is the DR, but you want router 1 to do it. All right. So now we've got that set up. And if I look at my routing table again, I can see which routes I'm learning. So that's on router 2. Let me just check on router 1. So on router 1, I'm learning the loopback addresses of router 2 and 3. And I'm learning this other address. Now this is quite interesting because I'm learning it via 2 different gateways. So this is in essence ECMP as well. And that is something that you should notice about OSPF and even other routing protocols. If the cost is exactly the same for a destination, then it is going to set up an ECMP route and it will do load balancing using ECMP. But perhaps you don't want load balancing to occur. So in that case, what you could do is you could just change the cost, make it cost more for one of the paths. And then in that sense, it will then prefer the least or lower cost network. So let's quickly do that. And I'm going to achieve that. Let's say we want router 2 to be the primary route. So to get to 192.168/30, we want router 2 to be the primary. So for that case, I'm going to go into router 3 and I'm just going to increase its cost. So it costs more for anything on router 3 on its interface. So I'm just going to say its cost is now going to become, let's make it 20. And let's apply that. And what I could also do is lower the cost on router 2. So let's go to router 2, go into its interfaces, and let's just make its ether 1 be a cost of 1. So let's wait for the OSPF to reconverge, get our neighbors back up. There we go. And if I look at my routing table now I have a single route to get to 192.0.8/30, which is quite cool because this means even if one of the routers go offline, even though you don't see both of the routes, the second route still exists. It's in the RIP. It's just waiting to be installed. But it's now preferring the connection between router 1 and 2 because we've set that as a lower cost and we set the cost higher to router 3. We'll also do a little bit of failover on this Ether 5 link, which you'll see in a little bit. I just wanted to kind of show you that ECMP exists there as well. All right. Let's quickly continue and do the default route advertisement because I've got a default route on router 1 to get out to the internet. But on router 2 and 3, if I look at their routing tables, I've got static routes to get out to the internet. And I dislike the static world, so let's fix that. So what I can do is on router 1, I can go to my OSPF, I can go into my instance, and then the instance I'm working on, I can set to do something with my default route. So I'm going to redistribute default route. Now you can select here, and then you've got as type 1 and as type 2. So we'll go more into the type 1 and 2 as well. But basically a type 1 route is going to be preferred over a type 2 route. Now I'll say I always, or let's say if installed. So I'll say if a default route exists, I'm going to redistribute it as type 1. I'm going to apply that on router 1. So I just made one single change on router 1. And if I go to router 2, we can see I'm learning a default route out using OSPF via Ether 1, which is awesome. So I can remove that static route out. And I can do the same on router 3. So if I look at my routing table, I've got a default route out. Let's just remove that. There we go. And let's test and see, do I still have internet connectivity? Let's ping 8888 and I can still break out to the internet. So that's awesome because now I've redistributed a default route from router 1 to my edge network so that these routers know how to break out to the internet as well. Awesome. All right. So what I'd like to do now is also just finish off this lab. by adding redistribution of these WAN uplinks so that we don't need to statically put them on the network. And this way our remote sites can also still have internet access. So I'm just going to do this by going into R2 and R3. So in R2, I'm going to navigate to my networks tab. And what I'm going to do is I can either put all of the WAN links as /30s here, or I can just use a summarized route, which I can make as 10.0.0.0/24, because I know all of the WAN links start with 10.0.0.0/30, 10.0.0.4/30, etc. So I'm just going to do this whole subnet. And what I'd like you to see is if I go to router 1 and I look at its routing table, we'll actually see that I am learning those /30 networks via Ether2 on router 2, and I don't need to statically put them in here. Let's do the same thing for router 3. So in router 3, I'm also just going to add a summarized route. So we'll make this 10.1.0.0/24 because router 3 starts with 10.1.0.0/30, whatever, for all of their WAN links. So let's apply this. I'll navigate back to router 1, look at the routing table. You'll see it will start updating because of the LSUs and LSAs and all that stuff that comes in. And there we go, 10.1.0.0/30. And this I am all learning via Ether2, but I'm learning it via 192.0.0.3, which is router 3's IP. So this is perfect. Now I've basically got dynamic routing configured between all of my routers using OSPF. I just want to have a look at the routing table on router 2 quickly. And I've got some static routing down to the LAN networks, but that we can fix with another video, or we can use some other type of technologies to make this work. Let's actually test and see if our internet out still works from our clients, because we haven't changed anything on our CPEs. So let's just check here. Can I actually log on to something? Let's try and get onto the Docker. I don't know why it's trying to download something there if I try to open the Docker, but that's okay. So let's just zoom in here. And then in this machine, I want to see, can I still ping 8888? I can. So I've still got internet access across the whole network. Even though we've restructured everything, there's no more static routes except to the CPEs. But on our core network on area 0, we're now just using, this is so cool, we're just using OSPF for dynamic routing. And now the whole network is alive. It's alive. It's actually breathing. It's starting to take shape as a living organism almost. Obviously it's not thinking, but it can figure out how to get between different points. And that is really powerful and really cool. I love it. I love it so much. Awesome. All right. I think this video is now starting to take a lot of time. I don't want you guys to feel burnt out. This is just to serve as an introduction into OSPF. There's going to be a lot more upcoming videos covering a lot more aspects, and I'll try and focus on very specific niche things next. So it should be a lot shorter videos, but I wanted to make it clear that there is a lot going on with OSPF, but it is an amazing protocol. And I hope you've enjoyed the video and the journey with me, and that you stick around for the next videos coming up, because it's going to be just as fun and interesting. So thanks guys, and thank you to all of the people that support the channel on Patreon and as YouTube members. You guys help really out a lot supporting the channel. I appreciate it. And I will catch you guys around. See ya. Bye.